Grazing your hand across a soft surface and listening to a concerto may not seem to have much in common, but in both cases the body is detecting and interpreting vibratory information. That vibration can be a result of the friction produced by the movement of your skin on a surface, by the movement of a bow on a violin, or by touching a speaker playing music. In this project, we seek to illuminate the physical aspect of sound perception by bringing vibrations directly in contact with the body. To begin to explore this concept, we created a first prototype of the multimodal harness, a custom-developed wearable device with 9 vibrotactile actuators integrated along the spine, on the clavicles, and on the ribs. We chose these particular locations on the body for vibratory stimulation for a few reasons. They provide musculoskeletal pathways for the mechanical waves to reach the inner ear via extratympanic sound conduction, also known as bone conduction. And their distribution on the torso allows for diverse spatialized audio-tactile effect design. During an exploratory workshop, we used the Max MSP software as an interface prototyping tool to create 3 preliminary composition interfaces for the body. The first interface is MP2P, or mono point-to-point, an interface designed as a creative tool for spatialization of multimodal signals on the harness by manipulating the signal's positions and trajectories. The designer first chooses a one-dimensional pathway on the harness that allows to route the signal across the positions of stimulation on the body. Then, they can create a spatialization pattern by manipulating the mono signal's waveform, amplitude, frequency, and position across the duration of the effect. The inner music interface allows the designer to self-set, adjust, and balance the volumes of each actuator's filter bands while listening to music. A high shelf filter attenuates all bass frequencies from the imported sound files with respect to the higher frequencies. Then, each actuator on the harness has a designated equalizer object, with 7 frequency bands to adjust between 50 and 4000 Hz. By changing the amplitudes of different frequencies, the designer can adjust the focus between auditory, tactile, and bimodal music perception. The drummer interface is a basic 9-track step sequencer and drum machine. Each track on the interface corresponds to one actuator and plays one selected sound file, imported from the user's library. The designer creates their drumming pattern by activating buttons on the sequencer, creating repetitive patterns of stimulation in which each actuator performs a sequence of an instrument. This tool is unique in that it transmits different signals to each position on the harness. During the workshop, we noticed a few key concepts and trends. Spatialized audio information is lost in extratympanic conduction, but the localized tactile perception can contribute to impressions of auditory source positions. Attention and expectations regarding the experience may affect users' judgments, who are comparing this experience to other systems designed for their ears, not for their body. Morphological differences may also impact signal perception. In future work, we will further study users' sensitivity and incorporate this data into more streamlined future iterations of the interfaces.